Good afternoon, everyone. Welcome to the webinar. My name is Inash Sheikh, and I will be your host for today. Before we get started, please let me take a few minutes to introduce EXPLIoT. EXPLIoT is an open source framework for IoT security testing, and it is the product of our experience and expertise in IoT security. At EXPLIoT.io, we build IoT security tools and target vulnerable devices for professionals and people who want to get into IoT security. We have cooked some amazing products in our labs. A few of them are EXPLIoT.io. It is an advanced hardware lab equipped with the best tools and equipment performing security evaluation of hardware and IoT devices. We have an amazing EXPLIoT store. It is an online store where you can find all our IoT security creation and other cybersecurity hardware. We have coded CloudFuzz. It is a scalable and distributed fuzzing platform designed to facilitate fuzzing open and closed source application on various platforms. We have recently launched IoT Auditor. It is an IoT security, compliance testing, and vulnerability management platform that empowers engineers to test and analyze different attack surfaces of the IoT ecosystem, like radio communication, firmware, hardware, IoT cloud, etc. We are sharing the community edition link on the chat box. You can also scan the code on the display and access the community edition. Today's webinar is on IoT hardware hacking, attacking I2C. I2C is a reliable communication protocol in an IoT device. I2C interface is always troublesome for an embedded developer. In this webinar, we will cover basics of I2C protocol, security issues with I2C protocol, finding out I2C pins on an IoT product, how to use EXPLIoT tools to identify I2C pins, sniff, and hack I2C chips. Our Honourable Speaker, Mr. Yashodhan, is an IoT researcher and compliance manager. You can check out this slide to see his accomplishment. At Paya2, Mr. Yashodhan is responsible for security assessment and creating threat models for IoT products. He's also working on achieving security certifications and accreditations for the organization. His current IoT security research focuses on side channel attacks and fault injection. Now, before I hand it over to Mr. Yashodhan, I request you to follow a few housekeeping rules. Please be on mute. If you have any question, write it in the chat box. We will answer the questions after the webinar. We will be releasing the recording of this webinar on our social media handle. So make sure that you're following us. If you're not, you can check out the chat box and follow us right away. Now, without further ado, let's get started. Mr. Yashodhan, over to you.
Thank you. So let me share. Can you allow me to share the screen, please?
Yes.
Is it visible?
Yes.
Okay. So welcome everyone to this particular webinar on I2C, right? So those who are working in embedded system development or any of the embedded security, you will understand the bracket, the ACK meaning of that bracket. Who doesn't understand, they will come to know that what does that mean over there. Now here, the agenda today is about discussing about the I2C protocol. We'll be discussing the fundamental things about the I2C. The reason being, if you understand any protocol properly, right, then there are many chances where you can innovatively think where the attacks are possible. The agenda for today is to understand this particular protocol, then what are the different attacks possible on this protocol, as well as we'll see kind of a video where we have demonstrated few of these attacks and how we can use some of the tools of the exploiter to attack on the I2C bus over there. Right? So this is the agenda. So to begin with, this particular I2C protocol, if you have ever come across this particular I2C protocol, I believe that it is one of the protocol which most of the embedded system engineers, face a lot of issues, whether you're in development or research, because it's kind of a protocol where there are many things involved and there are it's kind of a resource constraint kind of a protocol, I feel, compared to other protocols. So in the previous webinars that we have conducted, we had discussed about the UART protocol, the SPI protocols, and their security issues. Now, coming to this particular I2C protocol, it comes under the category of this synchronous communication. When we say synchronous communication, it means that we need a kind of a reference clock for that. Unlike the UART communication, where you have basically the receiver and a transmitter, you have the RX, TX pins along at both the side, and you are basically transmitting a data based on some kind of a format where the transmitter first sends a start bit, followed to that it sends a 5 bits to 8 bits of a data, and if needed it can add a parity bit and then a stop bit. So this is for kind of a one frame or one character it follows. Same thing happens again and again. So these things keeps on adding the overhead for that particular protocol. Now, to solve that particular problem, we use the clock. Out of the, for the synchronization purpose, we use something called as a clock, and the I2C protocol and SPI protocol are come under that particular category. The SPI protocol, if you have happened to be, watch this video or watch this particular and could attend this particular webinar on SPI, it was kind of a faster communication where you have these 4 dedicated channels or 4 dedicated lines, namely the serial clock, the master input data, master output data, what we call as a MISO, MOSI, and there is something called the chip select or the slave select, where I can connect multiple slaves from different pins of the microcontroller. But now coming over here, the 2 challenges that UART and SPI are facing is in terms of the extended hardware or in terms of the synchronization problem. When we are interested in looking for the reliable communication, where let us say one particular peripheral sends a data to the other one, right? And it wants a certain kind of acknowledgement whether the data has been, communicated properly, right? And in return, it gets a positive or a negative response from the receiver, right? So there, this particular I2C protocol a major role. Though this again can come under the category of what we call as a master-slave communication, where there will be one master, one slave, or it can be combinations of multiple masters and slaves, so that depending on the use case and the application that we have. But we'll try to simplify the things, keeping one master and one slave at the moment, and we can discuss on some of the use cases as well. So it's a synchronous communication with a reference clock, as well as it's a bidirectional communication. Now, this had been developed by the NXP Semiconductors, and most of the reference that I'm going to give is from the document. This is the I2C specification document, because whoever is the manufacturer of any microcontroller chips, and they have provided the I2C protocol in their existing microchip, on their chip or SoC, right? They need to follow this particular document as a specification, because that is something the base of that. Now, coming to the communication, though it's a bidirectional communication, unlike the SPI, it is basically the half duplex, where at the one time only one one can transmit over it. So in a way, you can see there are a lot of constraints, and there are only 2 lines of communication, where you can see there is a line for the data and that is line for the clock. Now, with these 2 things and using certain logics of the address, the I2C protocol can do wonder for certain type of communication. So let's explore this more and more. Now, if you look to understand the particular master-slave communication between the I2C peripherals, so as you can see, these are the 2 lines, and on these 2 lines, there are a number of slaves have been connected. So these slaves are getting the clock from this master, and as well as sharing the data over there. Right? then how do we differentiate between data and when the slave will get the data that is exactly that it wants, right? We'll come to that point in a subsequent slides. But you can observe there are certain registers connected over here, right, which are called pull-up registers, and they played a significant role when you design and work with the I2C. So in this particular master-slave architecture, the master is the one who always initiates the communication. Slave cannot initiate communication during the I2C, right? Master has to take that initiative part. So this is the first step in I2C part. Now, when we come to the speed of communication, so since here it is a kind of a communication where you need a lot of acknowledgement from the receiver part, right? So there are certain limitations on the speed of communications. So in terms of the embedded systems or an IoT product, this come under the category where you cannot expect a very high speed of communication, right? So though internally they have certain kinds of high speed mode, as you can see over the slide, right? But still they are limited because of the typical kind of acknowledgement kind of thing between the master and slave, and that's the what limitation on the I2C protocol. So standard like these are the modes of the I2C communication, and these are the data rates specifically given by the I2C specification by the NXP. And most of the time you will find the standard and the fast mode in which this particular most of the I2C protocol or the peripherals are working. So you can take an example of the memory chips, the EEPROMs, they are work with the I2C. Right? So there are certain sensors like accelerometer, temperature, they work with the I2C. Right? Then we also have some storage devices as well that work with the I2C part. So accordingly, many things where I'm interested in a reliable kind of communication, where I'm sending a data and interested to know whether that data has been reached there or not, I'll also certainly follow the I2C. Of course, one thing gets added over there because of the slow communication and those things, they are much more preferred in a scenario where I'm going for the low power consumed IoT devices over there. So most of the sensors and those things, they are basically based on those I2C protocol. Now, internally, what happens is like there is a need of kind of a pull-up resistors because there can be the combinations of multiple slaves, right? That will explore more in depth. But eventually, these two lines, where as you can see, if I go back into this particular slide where you have these multiple lines, and just imagine that I will like I know 3.3 volts of the input supply, and eventually I need to feed all those things, all those slaves, right? The power over there. So there will be challenges in terms of, you know, kind of the crosstalk between these two lines, because these are the two lines are responsible for whole of this I2C communication. So there are certain like we use some combination of resistors over there, right? Either in a series or a parallel kind of a potential divider to solve those problems of the loading, to avoid, you know, the delays between the communication. So what I'm speaking as of now will fundamentally link to somewhere where you'll understand, okay, this can be also thought as an kind of a parameter where one can go and attack the device as well, right? Okay. So now let us understand in what way this particular I2C communication happens. What is the start condition? What is the stop condition? How do that data is actually communicated? Right? So when we say this start and stop condition, here what I mean that we do not have kind of a start bit or stop it, right? Because that is a UART part of thing. Here we are working on a clock. The clock is something as my reference, and the start and stop condition depending on these two lines. So you can see the serial data and the serial clock. These are the two lines for me, and they are whole and sole responsible for the communication part. Now, just imagine that at one side we have a master and one side we have a slave. So making simplification, let us consider at the moment the microcontroller. Let's say we have a 32-bit microcontroller, right, which is acting as a master, and let there be a sensor or a memory chip on which, let's say, it's storing a data, or it can read data from a sensor itself, right? So it is considered as a slave at the moment. And then basically this particular microcontroller will actually now initialize the communication, right? It will actually as a master, and it will initiate that communication. How does it initiate communication? So by default, as per the I2C specification, as you can see, these two lines, serial data and serial clock, are logically high, right? By default, they're high. Now, when the master wants to initiate communication, what happens is, as you can see over here, this, first of all, this serial data line has been pulled low, right? As you can see, it has been a transition to the low phase, right? Logic low. And post to that, after a few instance, right, then particular this serial clock has been pulled low, right? So this is the initiates to start communication. Always remember, always the first line that has been pulled low from the I2C is always the serial data. Now, once it is done, the start condition of the communication has begun. So master indicating that, okay, I'm initiating the communication. And post to that, the serial clock has been pulled low. So logically, if you think why it is like that, where the serial clock is not pulled low and serial data is pulled low first. So the reason being, the data has been communicated over the this particular clock, and for that matter, the reference clock has to pull low. Otherwise, it will be misinterpreted that when I pull that particular clock as a low, right, it will consider to be the transfer of the data over there. And so what happens is, like, first we pull SDL line low and SCL low, and then it becomes the start of the communication. We'll see that in a moment. But again, when you want to again stop this communication, right, end the communication. So it is basically kind of a reverse way, where the clock is first pulled up compared to the serial data line, and then post to that, the serial data line is pulled up, right? So it's kind of a reverse way, start and a stop condition, and everything you can see with a reference to that particular clock. So this is the first state of the starting and the stopping of the I2C. Now, when we actually communicate, right, there are a number of challenges between the communication. Now, just imagine where I have, let's say, 3 devices, 3 slaves connected. Assume that there is a EEPROM, there is a sensors, and there is some other peripheral at the moment, right? And whole of them are connected over these 2 lines of serial data and serial clock. Then, if the master, the microcontroller, is sending data to one of them, how will you identify for which that data is? And we need some unique identifier for that. And this unique identifier is called as a unique slave address for that particular chip. So whenever any of the device that comes with any sensor or any peripheral that is coming with the I2C, what you call as the I2C bus interface, right, it will have certain specific address to that. Now, depending on the characteristics, it can either have the 7 bits or the 10 bits of address, right? Most commonly, you will find the 7 bits of address. So again, you will wonder why 7, why not 8? Because we have that standard of 8, 16, 32 in our standard thing, based on in a thought process of the logics over there, right? So the reason for that is the 7 bit of address, when we say, right, it means that the 7 bit of address for the identification of that particular peripheral. The 8th bit, that is for the communication, is used in terms of whether the master wants to write a data or master wants to read a data. And for that matter, that 1 bit can be considered as a reserved over there. So when the communication begins with the address, you set the read and write byte, and accordingly that communication can initialize. Now, also there is certain bus capacitance over there, because there are only 2 lines of communications, and there will be a lot of capacitance between these 2 lines over the PCB, and many factors are there. So this is kind of considered as a 400 picofarad as per the I2C specification though. Right? So these are the major things over there. Now, with this 7-bit address, logically or hypothetically, how many devices can you connect? So when we say 7 bits, if I make 2 raised to 7, it makes 128 combinations, right? So ideally, I can connect around 128 slave address over the single I2C bus on those single 2 lines, right? Practically, there are certain challenges to that, but yes, logically, I can say I can connect 128 different devices or the slaves across this particular thing, because each of every them can be identified uniquely with the address over there, right? So this is where the actual protocol begins over there, and this is where master will address a particular slave, right? So we understood the start and stop condition, we understood the address part. Now there will be number of bytes that has been transmitted, right? How many bits we are transmitting. So basically, as per the standard, similar to UART, we also transmit this 8 bits of the frame, right? And post to this 8 bits of frame, there is a request for kind of the acknowledgement from the receiver here, right? We won't say master and slave, but we expect kind of a acknowledgement from the receiver that, okay, I have received this particular 8 bits over there, right? So for that matter, what we do is like, to start with, again, the start conditions, SDA line pull low, SCL then pull low, 8 bits of data, the acknowledgement part, and then you again put those line lower, right? So this is what it happens between the I2C protocol. Now let us go in depth and understand how that acknowledgement and the data transmission actually happens in real scenario. So here to say, let's say there is a communication has begun. So this is the start condition. Now what happens is like, if you consider this particular timing diagram, what is happening? So here we can see like there are 8 clock pulses, right? There are the 8 clock pulses, and for each of every these clock pulses, I am sending a bits of a data. Now, after this 8 clock pulses, the transmitter is expecting kind of an acknowledgement. So initialize, what happens is like when the master initializes communication, it's not that we are simply sending a data, right? It's not like that. First, master will have that particular 7 bits of address, and the 8th bit is around the read and write part. So assume that for each and every clock pulse, right, we are sending this data of 7 bits of address and the last byte of read and write. Now once, or if this particular what we call as particular byte has been communicated properly to the slave, right, there is something called as an acknowledgement, right? And the slave will send an acknowledgement that, okay, I have got this particular data very properly, and you can continue with the next part. So this way, this communication has begun. And the same thing happens where you are again now sending actual data. So if let's say now the ball is at the court of the slave, where the slave is interested now, wants to share the data, it will basically send a 8 bits data and then wait for the acknowledgement from the master, right? So this way actually the communication can begin, or vice versa between the master and slave, right? Whoever is transmitting and who is a receiver part over there. Now, if that condition fails, if let us say this communication does not happen properly, right, then there is something called as a negative acknowledgement. So this is, I think, the most of you who have worked with the I2C protocol, when you begin, and even if you're professional at a particular point of time, you will see this particular knack happening over a period of time, right? So this kind of a pain for all of this embedded systems designer to see that particular knack signal, right? So this is where this communication begins, and once you are done with the data transfer, so the data continues again, 8 bits acknowledgement, 8 bits acknowledgement likewise. And then at the end, you have that stop condition where it wants to end the communication between the master and the slave. So same thing. If now, let us say I have 2 peripherals. Now, first of all, the job of that particular master is to read the data from the sensor over I2C. What it does, it will first of all choose the address of that sensor, 7-bit address, 8 bits of reading because sensor is only sending a data. Post to that, there is really acknowledgement from the sensors, and then there is a reading of the particular 8 bits of data to the microcontroller, and that way it reads the data. Now, let us say it wants to save that data into the memory. What will happen is it will basically kind of pause that particular communication, stop at the moment, and store that data over a different I2C channel, or possibly it's on the same I2C channel. It uses that address of the memory where it has a 7-bit of address. Let it be initiate between communication between the EEPROM, get a positive acknowledgement, and then store a data into that particular memory bank over there, right? So that way we can have the I2C based communication, right? For each and everything, always remember the AC key is the most important bit in that scenario. Now, then next part comes is like, how do we validate that this particular data has been communicated, or whether how do validate that, right? So for that matter, what this particular I2C specification says that the data is communicated when there is a change of the serial clock line. So as you can see over here that whenever a data line is stable, so meaning let us say I'm transmitting the data at the moment, and that time my serial clock line is high, 8 bits of data is transmitted, and then if I want to change the data, right, over there, right, what is to be done? I have to change the clocks itself, right, the polarity of the clock, and that way the data validation is possible over there. So this way I2C data gets validated based on this particular clock. You can simply just find out. So as you can see, if let's say the serial data is high, right? The serial clock at the moment is kept high. So meaning there is no change of the data. Now, when that serial clock has been pulled low, eventually it may be possible from 0 to 1, the data is from 0 to 1 or from 1 to 0. So change of the data is possible in that scenario. Right? So likewise, it happens for each and every clock pulse when you are sending the bits, right? So meaning, let us say this is a 1 bit where at this particular thing, I am sending, let's say low, right? The data is 0 when the clock is high, right? In the next thing, whenever have the next pulse, it is 0, right? I'll send the next bit of data. It's a let's say a 1 over there, right? So it's a reverse kind of thing, data change over there. So this way, I2C basically validates the data. Now, the next thing comes in I2C is about the stretching of the clock. So this is one of the challenge that happens in I2C communication. What does happen over there? So now the scenario where, again, let me go back to this particular scenario where we have this communication of this I2C, where the data has been sent, acknowledgement is there, that is perfectly fine. But again, if you go to the basics of it, the serial clock from the master is actually controlling that communication. Now, there may be the possibility that slave who is in synchronization with this clock may not able to follow this clock thoroughly, right? And there is a challenge for that. If what happens is like the 8 bits of data that has been communicated perfectly fine, right? The slave will send a positive acknowledgement. Now, think of the situation where the slave is not able to maintain that synchronizations, or it cannot hold with that particular clock signal, right? What will happen is like the clock is progressing ahead and ahead, but eventually after 8th bit, let's say it for the next bits of data, right, when we have acknowledgement and the data being sent again and again from the master itself, like what will happen is like the clock from the slave will not be able to handle that speed of the communication, and in that scenario it will consider that it is sending kind of a negative acknowledgement because it is not able to handle that clock itself, right? So that gives a false knack, I'll say, in that scenario. So it's a fail of the communication. So one feature that I2C specification provides is called as a clock stretching, where either a master or slave can actually pause the communication, can pause the I2C communication by pulling the particular clock line low for some amount of time. Right? This way, you have the sufficient time to have that particular 8 bits of data and prepare for the next byte of communication, where you are again getting a data from the transmitter over there, right? So that way, you are avoiding that knack condition again and again. The reason being, if that knack condition happening again and again, eventually are sending the same data, right? It is again affecting your performance of a system. So this is one of the important and critical feature in terms of the I2C. So that way, this is just like with this, what will happen is like you can, with a slave, you can send the SEK as well using that clock stretching part. So you can see this particular diagram where what happens is like you have this particular 8 clock cycles and there is a data that has been sent, right? So serial clock, serial data. And then this particular clock line has been pulled low for a certain amount of time, right? So practically they are holding this particular clock, what is called as a clock stretching. And eventually there is there is no kind of a knack, not negative acknowledgement at that time. So that way you can balance between the master and the slave communication. Now, so now next parameter comes over in I2C is about certain physical parameters that are associated with the hardware on that embedded system order. Now, when we have, let us say, this SD and SCL line, and you have connected your slaves over there, right? So it is always recommended that you need to have some kind of pull-up resistance. Right? This pull-up resistance will take care of some of the current requirements as well as something called as a time kinds of rise time requirement of the particular communication over there. Right? So we'll see that example. How does that happen? So as you can see in this particular slide, pull-up resistance is the something important when we come to I2C. Bus capacitance, and third is the rise time, because the three factors has been mentioned by I2C specification. If we do not follow them, either you are having kind of a design of an IoT product based on I2C, you'll likely to fail in a production grade scenario, right? Also, if you're looking from the perspective of attacking the I2C, make sure you understand these concepts very well, because if you are playing with those pull-up resistance, you can do certain attacks. You are working with the rise time, certainly you can do some attacks over there, right? So let's explore that in detail. So let's begin with the concept of the pull-up resistance, right? So on I2C bus, it is recommended to have two pull-up resistors, right? So what is the job of pull-up resistors, by the way? So basically it pulls up your voltage, holds on those particular voltage, and eventually make sure that all of the communication that you're doing with over a bus is getting sufficient current as well as sufficient voltage over there. This is the simple way of defining the pull-up resistance. Now, there are two resistance. One is the maximum and one is minimum resistance. And it depends on what. So as you can see, the formula given by that is like V bus. V bus here means that the voltage of your I2C bus. Generally, it is 3.3 volts. As per specification, I believe it is like 2.9 to 3.6 or 6 or something like that. But most of your sensors and those things comes around the 5 volts or the 3.3 volts that will certainly get over there. If you have certain kind of 5 volts devices, then you have to pull down the voltage and you do many additional things from the electronics perspective. Now, this particular voltage, right, kind of a VOL, kind of low kind of voltage, almost practically considered as a zero. And this is a load current, the initially very lesser amount of current. As per the specification, this VOL sets to be 0.4 volts and IOL sets like mentioned by this I2 specification is 3 milliampere. This is what they mentioned in their document. Now, again, the next part here comes is like the dependency on this current and this voltage is much more when we come to the resistance, the first minimum resistance. But what about the maximum resistance? So what is the mean and max qualities over there? When we go to this particular maximum part here, the dependency is more in terms of the rise time, right? And something called as a bus capacitance. Now, what does this rise time means? The meaning of rise time is nothing but, as you had seen those SCA and SCL line, where they are like going like, in a trapezoidal mode, it is increasing, making the level stable, and then it is coming down, right? So this trapezoidal part is like a rising of the edge and the falling of the edge. Right? Ideally, you can see like it rises within like at the same instant, sets up holds of the clock high, then falls off immediately, right? So that instantaneous thing in a practical scenario is not possible, and that's why that particular rise time and the fall time has been specified at that particular scenario for the clock as well as the data, right? And this is mentioned to be around 1000 nanoseconds, right? And there is something called as a bus capacitance. Now, based on these two factors, right, we actually decide what will be the minimum and the maximum amount of pull-up resistance, right? So now here again, I'm giving kind of a hint to you that what kind of attacks are possible, where if I'm trying to change the existing pull-up resistors in a product, right, with some other resistance, whether it's a high or low, right? What you're doing is like you're playing with the rise time and the bus capacitance over there, right? So let's understand first bus capacitance. So if you see, let us say I have one master and multiple slaves. Now, since we have these only two lines, there is a lot of dependency on these two lines to drive sufficient amount of current to the rest of the peripherals over there. And there it comes that at each and every point, you will see there are a lot of capacitance, the intrinsic capacitance. Also on PCB in which they have been mounted, there is a capacitance. Even the length of the lines add some capacitance. The difference or the what you call as a distance between these SD-SCA lines also add some capacitance. So likewise, all these capacitance added together, it will affect the communication. Why does it affect? The reason being, there is a combination of the resistors and the capacitors. And when we say this R and C combination, what we call as a time constant with the RC factor, right? So if you have studied the 555 timers and those things, you have seen that RC plays a major role in the time factor of any of the pulses. Now, coming to the next level, where this will also affect is about the rise time of that particular what you call as the communication. If you see on the left part that we have this either SC or SDA, sorry, SD or SCL line, where you can see at particular point there are two levels of threshold, 30% and the 70%, right? As per the specification of I2C, it says that when I want to communicate between these two guys, between the master and slave, at least I should have the voltage value, right, more than 70%, right, more than the 70% of that. Now what will happen is, let us say if I have the higher amount of bus capacitance or higher amount of, let's say, what you call this resistance over there, what happens is that I have the direct impact or inverse impact with the RC time constant. Eventually, if I have the higher resistance and the higher capacitance, and if you consider the timing is inversely proportional to 1 by RC, what will happen? My voltage that is increased over there period of time will be less than actual 70% of it. Meaning, if you just consider here, I have the maximum voltage of 3.3 volts now. Okay, I want to have the 70% of at least 70% for making sure my rise time is within the limits. So if you see this 30% to 70% of this particular slot where I have, it is given for that TR, that is the rise time, right? If it is not falling between that thing, the I2C communication is not going to happen, right? So here, if you observe, if I just take a 70% of 3.3 volt, it comes around 2.33 volts, I believe, right? 2.33 volts. But here, if you observe the voltage itself, right, the rise time is within below that particular limit, and eventually you can see the voltage itself is not leaving the 70%, and that way you will tend to get kind of a negative acknowledgement, right, if you are communicating with the slave. And these are the actual factors that you will see when you work with the I2C, right? So small factors, but makes a lot of sense when you are playing with the I2C part, right? So in short, what things are affecting your communication on I2C? The pull-up resistance, right? The rise time, the capacitance over there, right? On the specification part, of course, they say that 400 picofarad is something recommended as a capacitance of the bus. But of course, there are certain challenges that you have to look from the PCB part as well, right? But make sure that when you have such kind of negative acknowledgement during the I2C communication, always check at those basics. Where are you really working properly? Is your resistance what you call as pull-up resistance are within the limit? If you are putting it high, you are going to make make sure that things are not working properly over a period of time. And this will become worse if you have the multiple slaves in the scenario. Now, still there are more common challenges that you can see in I2C, and these are again as if you focus, you'll able to solve those problems with the I2C. So one is something like generally some of the let's say ST microelectronics or the Nordic semiconductors, I believe, right? So what they give is they also give an option of internally they have the pull-up resistors, right? So through programming you can actually activate them. If not, in some scenario, people doesn't do that. And eventually you try to, find out, okay, why my I2C bus is not working? And eventually first need to check out on your SD and SCL pin, are you seriously getting those voltages or not? If you're not getting, one chance is that you are not activated the internal pull-up resistors, first part. Then the most common part, the ACK failure, the acknowledgement failure that you get, right? So here, are you sending a data to the proper slaves, right? So if you are mistaken with the 7 bits of the data, it's possibly that you have like wrong address, you're not getting the particular acknowledgement. Then it comes about the what you call as in different scenario, we have those I2C initialization registers, I2C control registers, like I2C status registers are those internally there in the data sheet. And in the slave, basically what you have to do is basically what enable that particular ACK features. Some people doesn't do that, and again there is a challenge that you don't get the acknowledgement properly. Same thing happens when the master is not producing clock. In that scenario, you'll have to make sure that you set certain standard frequencies over there in the I2C peripheral, as well as make sure that the multiple pin functionality, because there are certain pins who are either working as the GPIO by default, they can also work as I2C, they can also work as a PWM. So are you using the proper functionality of those multiplexed pins over there, right? So if you address those things, your I2C works perfectly fine, right? And this is again indication that you can think of such attacks. Now coming to the actual attacks, right? What type of attacks are there in the market, right? So as if you just found around, right, you won't find the exhaustive kind of attacks that is happening over I2C. But yes, there are few of them which is associated with kind of a memory or some of the peripherals over there. We'll see what are the actual existing attacks possible over there. So one is you can actually sniff the signal. You can basically take a logic analyzer and connect between your master and slave, the I2C based master and slave. And eventually you can actually see the data. You can tap into this serial data line and the serial clock line and see the data patterns over there. There you will see a lot of things. You can see that clocks over there on each and every clock, what type of data is being communicated, then how we are getting those ACK features, how we are getting the NAC features, and those things, everything you're able to say to the sniffing part. Then signal manipulation part. So where what happens is like you can kind of inject a bit in your I2C communication and fool a system. That is way possible. Then there are certain peripherals that comes with the I2C, like these particular memory chips, right, where you are storing a data in EEPROM and you are communicating at those addresses, right? So there, basically, if you just desolder that particular memory and try to extract the either firmware or data from that, that way you can also have an attack on your I2C peripheral itself. And similarly, you can actually manipulate the data and pack the malicious code or thing, and again solder it back. That way you can do things, right? So clock glitching is again one thing, but here we won't discuss that. You can refer this particular link to read about what type of research is done in a clock glitching from I2C perspective. Right? Now, I'll consider, like, let's discuss this particular case where you can see kind of an attack that people have done over there. She's called as a bit injection. So what happened over there is like, so there was a kind of a radio receiver, radio trans receiver, and it had a particular 24C 64 series of this particular EEPROM, right, having the I2C peripherals. Now, out of this, it had basically 8,192 bytes of the addressable locations, right? So I can have 8192 bytes for the addressable banks for that. Now, there is a next series of this, which comes with a 224C512, right? And there, what happens is it has basically the 3 banks of this particular data. Now, the difference between two is like the addressable limit of this particular first one of 24C, what we call as 64, had a limit of like 0, 0, 0, 3 zeros and rest of 13 ones, right? So this was the limit. So consider the 2 bytes of the data that is addressed to be communicated. And out of that, the limit is like the 3 leading zeros and rest of 13s are trailing ones, right? So this is the limit of that. Now, what people had done is like both of these particular ICs, the 24C64 and 24C512, right? They had basically the same footprint, but the difference is like 24C512 has the more addressable memory. Okay? Now they have replaced that 64 by 512. The next challenge happens is like the firmware is addressing only those parts, correct? 8192 bits. So how can fool it? The idea was they had used something called as a 80 tiny microcontroller, right, for sniffing that particular I2C bus. Now, whenever that particular what you call as this particular SDL line was going low at the moment, it was sniffed, and through some interrupt, that 80 tiny 85 had a particular interrupt pin. It was making it high, right? The SDL pin, they are making it high, so that it considered to be the injected bit of the serial data. And that particular bit injection is considered to be for another address slave address over there. So that they addressed, instead of 1 memory bank in the chip, they address the 3 memory banks, right? So that way you have the more amount of memory available to you, and they had more scanning of like, so the storage into that memory was basically the stations, the information about the stations, radio station, they will scan and storing the data of that, right? So accordingly, they played the attack. So you can see about this attack, read about this in detail. So this is one example of how the I2C attack has been done, right? Now there are certain tools and frameworks that you can use to do such attacks over there. So from EXPLIoT, you can see we have the EXPLIoT framework as open source. You can go and download, and it has a plugins for that. We'll demonstrate that in a moment. Then we have some Diva board, we have Bus Auditor Nano. Out of that, the EXPLIoT Bus Auditor, what it does is like, for example, let us say I have an IoT product, and I'm interested in, first of all, finding out I2C pins. Assume that there are a number of sensors, but I don't know which pin is I2C, which pin is ZTAG, which pin is UART, right? So this particular guy helps you to find out which pins you are targeting over there. And if you're, let us say, targeting the I2C pin, which will also help you to find out, okay, out of this particular 10 number of pins, which is your I2C pin as well, right? So this will be the first step when we go for any IoT product. Use this Bus Auditor, determine which pin is I2C. Next part comes is like using something called as a EXPLIoT Nano. What this do? This is kind of a hardware device, which is a kind of a multi-protocol converter. Right? What it does, it supports basically the UART, it supports I2C, it supports SPI, ARM SWD, and the ZTAG. So what else you need? So basically you have all these peripherals ready, and if you want to debug into that and attack in any of this UART, SPI, I2C, or SW ZTAG, that matter, right? You can directly go use the EXPLIoT Nano and attack over there. Right? So this is one way you can use this whole EXPLIoT framework, Bus Auditor, the Diva board, and the Nano to have those combinations and understand how the I2C attack works. Now let us see the demo. Let me play the video for that matter. So give me a moment. I hope that is visible. Let me know. Right. So
yes, it is visible.
Yeah. So this video is made by my colleague Shakir. Right. So let me just let me again begin with that. Let me explain what is things over here. So as you can see in this particular video, there is this particular EXPLIoT Diva board which is played over here. What it does, this particular board is a vulnerability board. So you can learn about certain challenges from I2C, the hardware challenges like I2C, SPI, ZTAG kind of things, how you can extract the firmware, how you can attack on certain kind of protocols. Then it also has some firmware labs. Many things are there, right? So it is also a ZigBee kind of protocol, right? So here we have some I2C peripherals, right? At the moment, now we have this Bus Auditor. Now with this Bus Auditor, will determine which pins are I2C and what are their numbers, right? So let's begin with that. Right, so let's power up this Diva board. And power the Bus Auditor. Now, one thing that you need as a common is about the ground pin. We have demonstrated how we identify ground pin in our previous webinars. So if you go to our EXPLIoT webinars, you will see the UART to shell webinar where we had demonstrated how to find the ground pins with that. Now, out of the 16 channels, we are interested in 2 channels of I2C, the serial clock and the serial data. So that's what he's connected. So he has identified kind of the combination where I can have I2C. He's connected multiple pins over there. Now we'll go to the EXPLIoT framework, the open source EXPLIoT framework. And let us see what type of what we call as a list of the plugins. So you can see this complete list of plugins available. So whether it's a BLE or kind of a CAN, the Bus Auditor, the COPE protocol, the I2C, right, SPI, Those things are available in this particular framework. Now, our interest is now I2C as well as Bus Auditor. So with Bus Auditor and I2C, we are scanning what are the pins. We have to mention the voltage because 3.3 volt is something that we are working on. So there are certain commands that if you just go and see the help, you will get to know. So now, if you look over here, he has found two devices, I2C based devices, right? Out of which, let's say, choose this 0x480. So this is kind of the slave address for that particular device. And you can see the SCL and SDA number, right? So pin number 1 for this, pin number 2 is SCL and SD. Now, once we identify this device, this particular thing, now next part is to attack on that, right? So we want to basically extract kind of some information, kind of a credentials, let us say, from that, right? So now the job of the bus auditor is done. We will, first we have to identify which pins are connected to those pin number 1 and 2, right? So that's what he's showing over there. So you identify which pin is 1 and 2 physically on that particular board. Right. So we'll take now EXPLIoT Nano. Now our job is now to read that particular I2C pins in depth and understand if anything we can find interesting. So for that we'll use now the EXPLIoT Nano. Right. So there are certain pin combinations. So if you go to the website and see what EXPLIoT Nano pin configurations are, you'll easily get that. So we'll connect those pins where we identified this pin number 1 and 2. Let us now power up the Diva board again and connect this EXPLIoT so that you can access this through serial. So let us look for the plugins for this. Right. So I2C, so you can see I2C generic read EEPROM, right? So there is scanner is an EEPROM. I want to read something. So it has scanned, it has passed this thing. Now run this particular plugin, read EEPROM. So with the help, you'll get what things, whether you want to write something, read something, those things. So this is kind of a chip number for that particular EEPROM. What he's doing is he's trying to read from this particular thing and write whatever the binaries over there into his desktop folder. So we save it as binary data. So we can read about all the information about this particular chip size, byte size, those kind of stuff. So now he has come out of the EXPLIoT now, and let's go to the address, the directory where he has done it. Right? And with the strings utility, you can simply read this particular binary. So as you can see, there was something written as admin. This is, you can see as a password for that, right? And now, considering this password, if I want to access this particular I2C peripherals, right, and do the attack on that, what we'll do is like using the serial terminal, go to this Diva board So this is a serial command of accessing this particular Diva board that we can get access. So this is Diva. This is a list of the labs. And then for I2C lab, they want a password. So this was the admin, and we are granted access. So likewise, this attack is successful. Right? We extracted the password from this I2C, sniff it, and you can basically get access to the I2C part, right? So this way I2C attack can begin. So you can explore more on this way, or you can also look into some from the fundamentals that we discussed and think over it, right? So that's it from my side. Thank you so much. Any questions, please let me know.
Thank you, Mr. Yashodhan. I hope this webinar was insightful for everyone. Well, as promised with you all, we have something more and something exciting for this webinar. We are running a quiz competition, and the first 3 winners are going to win exciting prizes. We'll be sharing the link on the chat box. Please click on it, participate, perform your best, and try to come in the first 3. All the best to every participants.
Acariciarte y ponerte a dormir. Es escalofriante tenerte de frente, hacerte sonreír. Daría cualquier cosa por tan primorosa, por estar siempre aquí. Y entre todas esas cosas, déjame quererte, entrégate a mí. No te fallaré, contigo yo quiero envejecer. Quiero darte un beso, perder contigo un tiempo, guardar tus secretos, cuidar tus momentos, abrazarte, esperarte, tenerte paciencia, tu locura es mi ciencia.
Everyone, please share a thumbs up on the chat box as soon as you are done with the quiz so that we can move on to the next session.
Disfruto acariciarte y ponerte a dormir. Es escalofriante tenerte de frente, hacerte sonreír. Daría cualquier cosa por tan primorosa, por estar siempre aquí. Y entre todas esas cosas, déjame quererte, entrégate a mí. No te fallaré, contigo yo quiero envejecer.
Let's move on to our next session, which is a Q&A. If you have any doubts, please feel free to ask it on the chat box. We'll be answering it right away. Do we have any questions? So we have one, Mr. Yashodhan, is the MCU communication always, one second.
Almost you can convince, not always, but yes, most of 99.90% it is the must. Provided what type of architecture do you have. If you have a simple master slave architecture with master, one master slave, most of the time it is there. If you have, let us say, kind of a multiple master, multiple slave architecture, it may be possible that one microcontroller can become the slave as well. Okay,
Ashil from Benin, he's working on a project, security of IoT-based irrigation system in agriculture. And he need to have a best understanding of actual architecture and be able to propose more secure. So what are the resources available to help him? If you can suggest anything.
Okay. So resources, if you can start looking from the perspective of, if you look at our EXPLIoT things, we have the free ebook where the different attacks and those things have already been considered. You can download it for free. Also, you can look at different blogs that we have written. So there you will get holistic understanding of different attacks happen on the IoT system. And then you can look in further that how you can mitigate those attacks. I think that should be enough to begin. What you can do later is you can email me as well, right? Personally, and I can take you, like, help you on out as well. Right? So that should be the point.
Any other questions? What are the statics? What are the static about attacks in agriculture a few years ago?
The question is not much clear to me. Statistics. So I'm not from the agriculture background, so I don't much know about statistics on that. I'm really not sure what exactly you're referring to. You can personally contact me over email, right? I think that should be sufficient for that. And again, to answer that, the attacks happening on their agriculture, first of all, we need to understand what type of architecture that you have used from the development perspective. That also come into the picture. And as well the use case as well.
I think we have that many questions only. Thank you, Mr. Yashodhan. Everyone, we also have one more announcement. We are running a CTF. Once again. We are running a CTF for Hardware Legends. So if you are a hardware geek, make sure you are registering for this special CTF. Just click on the link we are sharing on the chat box and register right away. I would like to thank you all for joining us today. And we will be sharing the recording on our social media channel. So, and also announcing the winners of the quiz on our social media. So make sure that you're following us. If you're not, just follow us right away. Thank you for joining and thank you for giving your time. Have a nice day, everyone.
Thank you, everyone.